Hi there, Zach. Welcome to lesson number 84. And today's lesson is going to be super fun. It's going to be super radical, actually, because we're going to talk about multiplication of radicals. And if you don't know, people that are old like me, it used to be really cool to say radical or that's rad, man. Anyway, that meant cool back then. Okay, that's what radicals mean. But in your situation, a radical means a square root sign, right? Okay. Anyway, we're going to learn how to multiply those. But first, yesterday at 8 o'clock, it was very time consuming, especially when I went back for seconds. Okay. When you stop laughing, we can move on. And I'm going to remind you of the Poser rule. And if you don't remember the Poser rule, I don't know if I even called it the Poser rule, but if I didn't, I should have, because it is the product of square roots rule. And that's the rule that lets you do something like this, where the square root of 50 is the same thing as the square root of 5 times 5 times 2, because 5 times 5 times 2 is 50, of course. And then you can turn that into the square root of 5 times the square root of 5 times the square root of 2. And of course, when you have two of these multiplied by each other, it basically just becomes a 5. So that becomes 5 times square root 2. And that's how you simplify the square root of 50. And so that's the Poser rule. And I'll write, here it is in a different form, the Poser rule, product of square roots rule. And I put a bunch of M&Ms because they used M's and N's. These are not M and N's. I know they're not M and M's. It's just two M's, but still, it reminds me of M and N. M and M. Okay, so the square root of M times the square root of N is the same thing as the square root of the whole thing, M times N. And vice versa. This is what we just did. We had the 50 here, and we turned it into 5 square root 2, or the square root of 5 times the square root of 5 times the square root of 2. So we were doing it this way, but you could also do it backwards and do it this way, where if you start with like square root 5, square root 5, square root 2, that's all going to be equal to square root 50. Bam! Poser rule. Okay? Fun. All right, so this is going to be super fun. So we can use this rule to multiply radical expressions. These are so rad. So what if we have square root 2 times square root 3? Well, you can turn that into square root of 6. And it stays radical. That's why I put this. Stay rad. The radicals stay radicals. The coefficients, of course, stay as coefficients. So let's do some examples and you'll get the idea. This is example 84.1 on the next page, on page 346, and it tells us to simplify this. 4 square root 3 times 3 square root 2. So they say, well, I'll do that. Okay, they say that you can rearrange it if it's easier for you, where you just take the coefficients, 4 times 3, and then you, just changing the order, multiply the radicals, square root 3, square root 2. Okay, so the rule told us that we could do square root 3 times square root 2 is going to be square root 6. And of course, we can always do 4 times 3. So that's going to end up being 12 square root 6. Haha, isn't that super satisfying? That was fun. That's the answer. So the coefficients stay coefficients. The radicals stay radical. Stay radical, man. Okay, let's do another one. Look at this guy. That's rad. Looks like he just walked out of the 80s. Yeah, we used to say that. It's cool. It's rad. I think you should try and bring it back all on your own. But only use it when you're referring to radicals in math. That'll be funny. Okay, let's do example 84.2. They want us to simplify 4 square root 3 times 6 square root 6. Again, they rearranged it. If you can skip this in your head, you can probably skip it. But, you know, whatever. So 4 times 6 is just going to be 24 times the square root of 18. So there's that answer, but you can actually just take this part and break that down further. Let's do that in a different color so it's not confusing. Square root of 18 is what? It's going to be, square root of 18 is the same as 9 times 2. And the square root of 9 is 3. So that's going to be 3 square root 2. Okay, so this, I can put 3 square root 2 in the place of this. Okay, so it's going to be 24, because now I'm using this 24, times 3 times square root 2. What's 24 times 3? It's 72 times the square root of 2. Because you kind of want to have the number in here in the lowest possible square root number that it can be. You don't want to like leave it as 18 because that can be simplified further. Okay. All right, so that was fun. Maybe not as fun as the first one, but still rad. Okay, let's do example 84.3. And they want us to simplify this bad boy. All right, so this is a tricky one. And just like any number that you're multiplying by something inside the parentheses, you have to use the distributive property. So it's going to be this times this, and then this again times this. All right, so first steps first, let's just multiply it out and see what it looks like. Okay, so it's going to be this times this to begin with. So that's going to be 4 times 5, which is 4 times 5 is 20 times square root 3 times square root 2. Okay, and then I'm going to add to that this times this. So 4 square root 3 times 6 square root 3. Okay, so it's going to be 6 times 4 is 24 times square root 3 times square root 3. Oh, that's going to be able to be simplified because square root 3 times square root 3 is basically like just like doing square root 3, that whole thing squared, and then it just simplifies to 3. So it's going to be 24 times 3 right there. All right, so for the first step, it's going to be 20 square root 6 because I can use the Poser rule and do this times this. And that's a pretty low number, so I'm going to leave it like that. And then I'm going to add 24 times 3, which is 72. And that's it in its most simplified form, because this is kind of like an x. You can't combine these anymore because they're not like terms, right? It's this plus this. Okay, cool. Final answer. Let's do example 84.4. Ooh, this is rad. Check out this. Whoa, what is that, a dolphin or a shark? No, I think it's a dolphin, right? He's surfing with dolphins. Totally radical, dude. Okay, let's do example 84.4, and it's basically another one where we're going to have to use the distributive property, this times this, plus this times this. Okay, so let's just multiply it out. First, this times this. So I'm going to get 12 because I just multiplied the coefficients, 4 times 3, and then square root 2 times square root 2. Which I'm just going to simplify that right now because there's 2 of them. So it's just going to end up being times 2. 12 times 2. And then we add to that this second part, which is going to be this times this. So let's multiply the coefficients first. So it's going to be 20 times square root 2. Okay, so 12 times 2 is 24 plus 20 square root 2. That's it. I think that's the final answer. Yes, and that's what they got in the book. So we're all on the same page. Sweet. Okay, now this is where the lesson really gets fun because we get to talk more about functions. Functions are super fun because they're like machines. Okay, so remember, they're like the vending machines of math. So functions are the vending machines of math. So we can think of an algebraic function as a function machine. I did this in the previous lesson already, and then they did this after. It's like they copied me. I thought it was my idea to make it like a machine. Anyway, here's what's going to happen. This is the machine, okay? This is the function machine in the middle. You're going to put in an x, and it's going to spit out a y, okay? So what you want to have happen is anytime you put in a specific value for x, you get a very specific y that only goes with that value. You don't want to put in $1 and then you can either get like a candy bar or cookies or something else. You want to know what you're getting, man. So if you put in a 2, then this is the function x squared plus 5. So it is definitely going to spit out a 9. Every time you put in a 2, it's going to spit out a 9, and that's perfect. So for every specific input, there's one specific output, okay? Now, if you put in a 4, then it's going to give you x squared plus 5. It's going to give you a 21. Sweet! Now, what if you put in a 7? It's going to give you a 54 once it goes through that equation. Now, it's okay. Let's say you really want a 21. It's okay if you put in a 4 or if you put in a different way to make it equal to 21, like maybe a -4. That's fine. That's fine. It's still a function because either way you get your candy bar and you know what to put in so that you get your candy bar. What you don't want to have happen is every time you put in a 4, it's going to give you, maybe this time it'll give you a candy bar. Maybe next time it'll give you donuts. And you're like, no, I want a specific thing for everything for every value that I put in, right? So that's what makes it a function. If you get a certain thing for every value that you put in, that makes it a function. All right. So we're going to talk about some things that are functions and some things that are not functions. So this first one, this example is on page 347. And is this a function or is it not a function? So all you get from this vending machine is a 3 every single time. So you can put in a 4, but you'll get a 3. You can put in a 2, but you'll get a 3. Now that's fine. It's still a function. Why? Because maybe it's a vending machine that only sells Coke, right? And maybe you can put money in, a couple different ways. Like you can either put in 4 quarters or you can put in 2 50-cent pieces, whatever. Either way, you're going to get your Coke, and it doesn't matter what you put in, you'll get your Coke, and that's fine. So that is still a function because you know what you're getting. Now, is this a function? Here's the domain on this side is the domain. Remember, the domain is what you put in. And here's the range on this side, and this is what you get out. So it doesn't tell us, in this situation, the machine is gone. It doesn't tell us what the function is. But that's okay. We can still figure out if it's a function or not. Okay, so if you put in a 4, it gives you a 3. All right, that's fine. Maybe I want a 3. If I want a 3, I'm going to put in a 4. If you put in a 2, it's going to give you a 5. That's fine too. Every time I want a 5, I'm going to put in a 2. And if you put in a 1, it gives you a 6, and that's totally fine. So no matter what I put in, if I put in 1 quarter, 2 quarters, or 4 quarters, I'm going to get something specific. You can think of these as ordered pairs, x, comma, y. So if I put in a 4, it's going to give me a 3. If I put in a 2, it's going to give me a 5. And that is a very specific dot on a graph. It's a very specific image. So no matter what you put in, it will give you an image. That's what it means when you read that in the book and it says there's one image that goes for each domain. That's what it means. It's like a dot on a graph. If you put in a 1, it's going to give you a 6. And that's very specific. And so this works as a function. Is it a function? Yes, it is. All right, what about this one? Okay, so here's the domain. Here's the things you put in. And here's the range. And again, it doesn't tell us what the function is, You know, it just wants to know, is this a function? Now, let's look. In this situation, if I put in a 4, I'm either going to get a 3 or a 5. I don't like that because if I put in 4 quarters, I don't know if I'm going to get a candy bar or if I'm going to get chips. Like, I want one specific y for every x. There has to be only one y for every x. If I put in a 2, it will give me a 6 every time, but I'm still not happy with this branching point right there. So this is not a function. And if it's not a function, it's called a relation. Think of it as a vending machine. Would you be happy with this vending machine if you put in 4 quarters and it gave you, it might give you a 3, it might give you a 5, whatever it feels like giving you. No, you would say, hey, it's not functioning that great. No, because it's not a function. It's just a relation. All right, so that's not a function. What about this one? This is actually not even a relation because check it out. You put in a 4, and whatever this machine is doing, we don't know the f of x, it's giving you a 3. That's fine. What if you put in a 2, it's going to give you a 5. That's fine. If you put in a 1, it's going to steal your money. It's not going to give you anything. There's nothing over here. This is like having an x with no y. An x with no y. An x with no y is like a broken heart. It's like you can't have that. That's like, look at Milhouse. He's throwing the frisbee to nobody. That's an x and no y. No, can't have that. It's not a function and it's not a relation. So no function, no relation. Okay. Now, if you don't want to look at the machine as far as domain and range, you can also just look at ordered pairs. And you can look at ordered pairs and say, is this a function or is it not a function? So, for example, if every time you put in a 4, you get a 3, and if you put in a 5, you get a 7, right? Because this is the domain, this is the range. So what we're going to do is we're going to look at all of these ordered pairs and make sure that it makes sense. Okay, so if I put in a 4, I get a 3. That's fine, whatever. If I put in a 5, I get a 7. That's fine. Every time I want a 7, I'm going to put in a 5. Makes sense? If I put in 9, I get a 3. Okay, cool. That's fine. If I put in a 4, I get a -5. Wait a minute. I already saw 4 up here. So if I put in 4 quarters or something, I'm going to get either this or this. No, I don't like that. That is not a good function. That's a bad function. It chooses for me. No, I'm not happy with that, so this is not a function. This is a relation. Okay, so this is not a function. And so when it asks us what it is, it's going to be a relation, not a function. I mean, they're all related to each other, but because of this and these two different things, it's not a function. You have to only get one specific y for every x in order for it to be a function. Okay, what about these ordered pairs? Are these a function, or is it a relation, or is it no relation? Let's look at them. Okay, so here we plug in a 4 and we get a 3. And here we plug in a 4 and we get a 3. That's fine, and it's totally consistent. We put in a 5, we get a 7. We put in a 9, we get a 3. Okay, now these y's are the same. Does that matter? No, because you can either put in 4 quarters or maybe you can put in 9 something, but if it equals $1, that's fine. It's still going to be, you're still going to get your candy bar that you want. So as long as there's a specific y for every x, it's okay if there's more than one way to get your donut, right? If there's more than one way to get your donut, that's fine. You just don't want the machine choosing for you. So if you want a donut, you can either put in a 9 or you can either put in a 4, but either way you get your donut, right? So that's fine. And there are 3 3s here, and there's a -3. That's fine, doesn't matter. And but all the specific x's have a specific y. So that's totally fine. I love it. This vending machine functions as a function. And I'm going to say, yes, it's a function. I like that vending machine. All right, now this was in the book, so let's go through it and make sure that we understand it. We use the word function. to describe a mapping. So when they say mapping, that means there's a specific x and a specific y. So it's a mapping from each member of the input set. So every time you put in an x, it spits out a y. The input set is called the domain, and it gets you exactly one member of the output set, which is called a range. There's one y for every x, okay? But there might be more than one x for every y, right? You can have as many x's as you want, right? Each member of the domain maps to an image in the range. What does that mean? It maps to a dot. It matches to an image. So if you've got a graph, there's your x and y. It's an image, okay? Thus, the word function brings to mind the following. Number one, the numbers that are acceptable as inputs and the algebraic rule, if there is one, that can be used to find the unique output that is paired with each input. That means that this is telling you about the domain. And the domain can be anything as long as you're not dividing by 0, you don't have anything over 0, and you don't have the square root of a negative number. Okay? So that's the rule. A table of ordered pairs of inputs and outputs where each input member is paired with exactly one output, and all equal inputs have the same outputs. In other words, you can have 4 quarters to get your y, or you can have $1 to get your y. It doesn't matter as long as each input gives you the same output. All right, a set of ordered pairs such that no two ordered pairs have the same first element and different second elements. So you can't have a 4 paired with a 3 and a 4 paired with a 7. No, that is a bad machine, because that means if you put in 4 quarters, it's going to choose for you. Do you want a donut or do you want chips? It's just going to choose. And I don't want that. I want donuts if I want donuts, right? Okay, what about the last one? The graph of the geometric points whose coordinates are the ordered pairs. The graph of the geometric points whose coordinates are the ordered pairs just described. Basically, you can graph a function. All right, so that makes sense. Let's jump into some more examples, and it wants to know, is this a function? Yes or no? Okay, I simplified the drawing. So, excuse me, if you put in a 4, it gives you a 7, fine. If you put in a 5, it gives you a 2, fine. If you put in a 6, it gives you 14. Remember, these are ordered pairs. 4 is going with 7, 5 is going with 2. It doesn't tell us what the equation is, but that's okay, it doesn't matter. Is it a function? Heck yes it is. That's great, because I know if I want a 7, if I want my donuts, I need to put in 4. If I want my chips, I need to put in 5. If I want my whatever, I need to put in 6. So that works. That's a great vending machine. I'm going to say, yes, this is a function. It's a function. Function. Okay. Why is it a function? Because there's one image and only one image for each member of the domain. So once you put in an x, then you have an image, because now you have 2 points, an x and a y. All right. Let's do the next one. 84.6. Is this a function? Now, this is looking a little bit concerning right here. Like, what is happening here? It's basically saying if you put in a y, you get a p. I'm okay with that one. That is, so far, we're a function. That's okay. If I put in an a, then I get an x. That's fine. I'm okay with that. If I put in an m, I get either an x or a 5. No, I'm not okay with that. I don't want the machine picking for me. I want to pick. So this part is the thing that says, nope, I do not want to buy from that vending machine. It's not a function. No on the function. Why is it not a function? Because there's 2 y's for that m. You can't have an ordered pair that is x, y, y. No, that doesn't make sense. If there were 2 different ways to get to x, like if this were gone, then that is a function, because I can well, this would have to have something. then this would be a function, because if I want my donuts, I can get it this way, or I can get it this way. Either way, it's specific. It's specifically going to the donut. But if there's also this to, I don't remember what this was, 5 or something, then we have to say no. I'm not going to that vending machine. I don't think you would go to that vending machine and take a chance, right? Okay, 84.7. Is this a function? All right, this vending machine only spits out 2 things. It can either be a 5 or an 11. To get to a 5, you can either put in an A or a 4. I'm okay with that. To get an 11, you have to put in a 7. I'm okay with that. That is a vending machine that still works. So I'm going to say yes, it's a function. Yes, on the function. Because the vending machine sells 2 things, and you can be specific. You can specifically choose which one you want. Okay, what about the next one, 84.8? This one's different. This says you put in anything, and you're going to get, it's not specified. The range is not specified, but the function is specified. So the f of x is x plus 2. So if I put in any real number like 3, that's going to give me a x plus 2, 3 plus 2. It's going to give me a 5. And if I choose any real number, then it's going to give, like even pi, then I'm going to get pi plus 2, right? So it's going to be something specific over here, and it's related to the domain, and it's specific to the domain. So actually, this is a great function. I'm going to say yes, this vending machine works, okay? Even though the range is not really specified, but the function is, so, and there's only one value of y for every x. So that's a function. All right, now 84.9, we're going to look at pairs. No, not that pair. We're going to look at ordered pairs. And it wants to know, are these ordered pairs a function? Alrighty, so there's only 3 of them. So basically this vending machine only gives 6s, 2s, and 5s. I see a problem, because if I put in a 4, I'm either going to get a 6 or a 5, and I don't like that. So this is not a function. No function. Okay, so A is no, because there's 2 different y's for the same x. No, no bueno. What about this one, B? Is this a function? This vending machine sells 8s, 6s, and 7s, and you can get to it specifically with a certain x. So I'm going to say yes, this is a function. This vending machine works. So yes, that is a function. All right, what about 84.10? We're going to look at some more pairs over here. No, not those pairs. These ordered pairs. Which of the following are functions? Whew. All right, we're going to be sick of looking at pairs after this. But let's look at A. So for now, we're going to focus on these ordered pairs. If you put in a 1, you get a 2. If you put in a 2, you get a 3. If you put in a 3, you get a 4. If you put in a 4, you get a 5. It seems like the function is x plus 1, right? So, but there is a specific y for every x. So I'm going to say, yes, this is a function. What about the next one? B. So now we're looking at these ordered pairs. You have, if you put in a 1, you get a 2. If you put in a 2, you get a 3. If you put in a 1, you also get a 3. And you already got a 2 for your 1. Nope. This is that. I don't like that. So because there's 2 different y's for the same input, I'm going to say no. This is not a good vending machine. No function. Alrighty, let's focus on this one. But it is a relation. So it's just called a relation because everyone is in a relationship. Okay, so let's look at this one. If you put in a 4, you get a 3. If you put in a 2, you get a 2. If you put in a 4, you get a 3. Again, so that's the same. That's consistent. If you put in a 3, you also get a 3. That's fine. That's fine. That just means this is chips, this is chips. If I specifically want chips, then I can choose whether I want to put in a 4 or whether I can put in a 3. So as long as I can choose, because I'm choosing what I put into the vending machine, then I can be specific about what I want. And that's fine. That vending machine is going to work. So I'm going to say, yes, that's a function. Okay, last one. D. Is D a function? So if I put in a 1, I get -1. If I put in a 4, I get -1. That's fine because I'm still choosing. I'm still choosing. If I put in a -1, I get a -1. It seems like I always get a -1, but that's fine. That's fine. I can still choose. But if I want a -2, I'm going to put in a 3. That's fine. This is a function because it seems like this vending machine only gives out -1s or -2s. But either way, I can still choose what I put in. So as long as I can choose, then yes, that is a function. I'm happy with that. Okay, let's do example 8411. Is this a function? 8411. All right, so actually, does this diagram, I skipped one. This is not 8411, this is 8412. Okay, I made a mistake somewhere. So let's fix this mistake right now. So this is going to go up here. And for 8411, they want to know, is this a function? So here are my inputs. Let's fix it right now. Here's my inputs. So my inputs are going to be either a 7 or a 6. And then what I get out is the outputs. Sorry, the yellow is hard to read, so I'm going to do it like this. Okay, these are my outputs that I get out. And it's either going to be, it's going to be 11. If I put in a 7, I get an 11. If I put in a 6, I get a 4, or I get an 8. I already don't like it. Because if I put in a 6, the machine chooses for me. I don't get to choose. So this is a no bueno. This is not a function. So I'm going to say no on the function. Now we're doing 8412. This is 8412. Is this a function or a relation? Okay, so if I put in a 6, I get a 4. If I put in a 7, I get an 11. So far, I'm good. If I put in a 5, oh, it steals my money. It gives me nothing. Gives me nothing. This is the poor Milhouse situation. So it is clear to me that the republic no longer functions. This is not a function. No on a function. No function. Is it a relation? No, it's not a relation either because poor Milhouse is not in a relationship. This is a lonely number 5. There's no relation, no function. Nothing. It's stupid. It's neither. All right. And that's it for this lesson. I don't trust those trees, son. Son? What? Why not? They seem kind of shady. All right. Okay, have fun doing your math, Zach. Love ya. Bye.